Hello, my name is Isabella Rangos. This is Lab 3, Exploring the Motion of a Star Orbiting a Black Hole. By generating a list of positions of the star at each time step, which is equal to 1 day, we can calculate the velocity of the star as it moves between each position. These changes in velocity allow us to calculate the net force, assuming the only force acting on the star is the gravitational pull from the black hole. By creating a computational model that calculates the momentum and net force throughout the duration of the orbit, we can use these magnitudes to calculate the mass of the black hole. Given a list of values for the mass, the average can be found and used as a good overall predictor for the mass of the black hole. We can also use these values to find the parallel and perpendicular components of the net force. The fundamental physical principles of this lab experiment include Newton's second law, which allows us to calculate the expected future position of the object given the forces acting on the object. Starting from the original data, the observed positions of the object can be used to calculate the net force between three different positions. The other fundamental physical principle of this lab is Newton's law of universal gravitation, allowing us to use the net force acting on the star to find the mass of the black hole. We also use Newton's second law, or the momentum principle, to derive the perpendicular and parallel components of the net force. The perpendicular component shows the change in direction, while the parallel component shows the change in magnitude. These distinctions apply to both the rate of change of momentum and the net force. We begin with the given observations about the star, that its mass is 2.0 e30 kilograms, and the time steps for each generated position will be 1 day, or 86,400 seconds. This is conveyed in the starting lines of the code, here and here. To set up the computational model to calculate the mass of the black hole, we start off by coding for the initial and final velocity at each series of time steps. These are then converted into momentum by multiplying by the mass of the star. Delta P, or the change in momentum, is equal to the final momentum minus the initial momentum. We then specify the rate of change of momentum by dividing delta P by delta T, the change in time. This rate of change for momentum is equal to the net force. This rate of change of momentum is equal to the net force. We then calculate the parallel component of the rate of change of momentum, which illustrates the change in magnitude. The perpendicular component is found by subtracting the parallel component from the overall dp dt. The parallel and perpendicular components of the net force are equal to the respective components of the rate of change of momentum. The arrow scale was selected to fit the scale of the computational model and was assigned to three different arrows in the model itself. First, the net force, then the perpendicular component of the net force, and finally, the parallel component of the net force. Finally, code is added to calculate the mass of the black hole. This reflects a rearrangement of Newton's universal law of gravitation in that the mass of the black hole is equal to the net force multiplied by the squared magnitude of the distance between the black hole and the orbiting star, all divided by the g constant times the mass of the star. Here we see the outcome of the coding, the computational model of the motion of the star's orbit. My computational model outputted 445 values for the mass of the black hole. I then averaged all of these values to get an experimental value of 1.83026 e34 kilograms. My computational model not only calculated the mass of the black hole at sequential time steps of the orbit, but also calculated the net force and its parallel and perpendicular components in newtons. In the case of this experiment, there is no difference between the net force and its parallel and perpendicular components, and the rate of change of momentum and its parallel and perpendicular components. This is illustrated in our derivation of the parallel and perpendicular components from the momentum formula and from our code. If the black hole from this experiment was replaced by a black hole with a different mass, but the motion of the star remained the same, we would not be able to calculate a new mass for the new black hole. Our entire analysis and calculation of the black hole's mass is based on the motion of the star. If the positions at each time step are the same, then we will get the same calculated mass of the black hole. In conclusion, the computational model allows us to generate a list of values for the mass of the black hole, which we can then average to calculate the predicted overall mass. We can also visualize the net force and its parallel and perpendicular components throughout the orbit, as well as compute overall values. These individual values were calculated using both the momentum principle and the law of universal gravitation.